Welcome to Cubes in Space. Today we're going to be talking about Module 4, Big Balloons Equal Big Science, and we're going to provide information on the launch location and details about the large-scale scientific balloon and the flight to near space. We'll also discuss the requirements and constraints for the experiments that will fly on the mission. The 39 million cubic foot balloon is partially inflated with helium. Those large tanks on the truck are filled with helium, and there are actually two of these trucks that help to partially inflate the balloon. The structure between the balloon and this large truck is the ladder, and hanging from the truck is the gondola, which contains our experiments along with NASA's instrumentation. And if you look in the background, you will see wind turbines, indicating that there's a lot of wind along the flat terrain in New Mexico. And this day was clear, sunny, not a lot of wind, so it was the perfect day for launch. This is the launch location in Fort Sumner, New Mexico. The launch location is at an old World War II airfield. Here on the runway, you can see Big Bill. This is the launch vehicle that's going to release the balloon to near space. And this was our first mission, RB-1. We flew on NASA's RADX mission, and it's looking down at Earth when it's at float. So at its highest point in flight, you can see the curvature of the Earth, the little bit of Earth's atmosphere, and the darkness of space. The next set of images show what the terrain in New Mexico looks like. It is considered a desert. You can see the large wind turbines that stretch for hundreds of kilometers. This provides a lot of energy to New Mexico. This also indicates that there are pretty strong prevailing winds for a lot of the year. Fortunately, during our time, the fall campaign in August and September, it's what's called turnaround, and it is a time of year between normal prevailing winds and the monsoon season where the winds do calm down and allow for good launch and flight. And you can see in pretty much every direction for a good 70 plus kilometers, or 50 miles in all directions. And in the very distance in the horizon, you can see thunderstorms that are starting to build, indicating there is moisture in the atmosphere. And typically it is coming up from the Gulf of California. Here you can see an example of wildlife at Fort Sumner, or it's also called the Fort. Here is a jackrabbit. There's also little bunnies with cottontails, so some cute wildlife. But some less cute wildlife also include tarantulas, scorpions, and rattlesnakes. So walking around the property of the fort, you really need to watch your step. Otherwise, it could lead to a very bad day. Now let's take a look at balloon testing day. This is the gondola, so this is what carries the payload. We are bolted to the side of the gondola. This is what's called the carrier or the suitcase because it does have handles on the top and the side. This is the heavy aluminum faceplate containing our up to 121 experiments. So the gondola, this one, I believe this was RB-5 mission in September of 2019. We did have, so the instrumentation that was on here, some were powered by solar panels. And on the right, you're seeing the Columbia Scientific Balloon Facility personnel that are conducting an electromagnetic interference test to ensure that all the powered experiments did not interfere with NASA's instrumentation. So this was the Long Duration Balloon Test Flight Mission, or LBD test flight, NASA's mission, and we were RB-5 in 2019. Another type of test is called the hang test, and both these tests occur a couple days before the launch of the mission. This is Big Bill. It is hanging the gondola, and it's actually weighing it. So the total payload mass, which included the gondola, our carrier, our experiments, 8 different experiments from other organizations, and NASA's instrumentation, plus all of the hardware and electronics, had to be right under 3,000 pounds, or about 1,350 kilograms. Big Bill is stored in this large hangar, and on the right you'll see the RVs and the Columbia Scientific Balloon Facility staff. They stay in these RVs as they travel either to Texas or parts of New Mexico or Arizona to retrieve the gondola and balloon once it terminates. It can often terminate in very remote locations, so they use RVs because it can take a couple days to get out there, and if they have to wait for permission from a property owner because the balloon landed on private property, they could be out there for another several days. So it can take up to a week for the experiments to get back to the fort once they land. This was our first mission. We were on NASA's RADx mission in 2015. We were a secondary payload, which is also called a Flight of Opportunity. And this picture is an official NASA picture. If you go to the Balloon Program Office website for NASA, you can see this image. And again, they are conducting an electromagnetic interference test. This is a smaller gondola than what you saw before, so our first flight was not on a 39 million cubic foot balloon. I believe it was on an 11 million cubic foot balloon, but we were happy to be on an official NASA mission. This is the RADx mission profile, so flight profile, and the flight profile shows you a lot of details about the flight from beginning to end, which is called termination. The RADx mission was based out of NASA's Langley Research Center, and this mission was testing different size dosimeters that could be placed in cockpits of commercial flights to detect the amount of radiation that commercial pilots are exposed to when they're flying from the US to Europe or Europe to Asia going near the North Pole. Here, it ascends for 2 hours in the daylight. It spends 10 hours at float or at apogee for nearly, then you can see that the sun is setting. And here it valves down, so it means that the helium some of it is released and some ballast is dropped. Ballast is the weight that is needed to keep it at a certain altitude. So it valves down for 2 hours in the dark, so this is nighttime. And then it's another 10 hours until sunrise, and then after sunrise, it's about 45 minutes to termination. And there is a triangulation of communication between NASA Langley Research Center, so Mission Control, Operations Center in New Mexico, and a satellite, and ground station, and the balloon itself. Next we have the view at float on the RB2 mission in 2016. You can see the curvature of the Earth, the atmosphere, the darkness of space. Here we are attached to the side of the gondola again, outward facing. And so every experiment does have full exposure to, in this case, it was the sunlight or space. And on the right-hand side, you're seeing this is RB4. We had a full carrier of 121 experiments. You can see the handles of the carrier, again, mounted onto the side of the gondola. And our powered experiments, we keep on the left upper quadrant of the carrier. It's easier for us to activate them, to turn them on. So between A1 and A6 and C1 and C6, this is where we keep the powered payloads. This is a really cool image that we don't normally get to see. This was with our RB5 mission at float. And this is a look up at the bottom of the balloon. So this was the first time out of 5 flights that we ever had this particular point of view. You can see the ladder, you can see the large arm and cables that attach the gondola to the bottom of the ladder. And this is another view, little penguin and alien. These are stuffed animals from the flight director that have flown on 7 different missions. Again, you can see the darkness of space that is surrounding the balloon. It's above the Earth here. You can see curvature and the atmosphere. So very, very cool picture. This shows the RB5 landing location, so at termination in Santa Fe, New Mexico in the mountains. Well, it was near Santa Fe. You can see how rugged and remote the terrain is. Again, it can take several days for the crew to get from the fort to the landing location. And if the balloon lands on private property, again, it could take several days for NASA to obtain permission to access the property and then to find the balloon and its payload, which does contain GPS tracking information. So again, landing near Santa Fe, New Mexico, very rugged. It's not as if you're seeing a road or sidewalk or anything to this location. And this is a reason why it does take several days, if not a week, for the experiments to get back to the fort. Then they pack everything up, and it could take several weeks to get from the fort back to NASA Langley Research Center. This is another view of the CSBF crew conducting tests 2 days before launch. So this is an electromagnetic interference test. This is inside the hangar, and you are seeing how large those helium tanks are that are attached to 18-wheelers. So 2 18-wheelers of all of this amount of helium for the 39 million cubic foot balloon. This is the launch vehicle. It's called Big Bill, and this is the crane that when Big Bill drives across the desert at a pretty good speed, this crane lifts up. The gondola that is hooked to the crane here gets released, and then the balloon just silently and gracefully floats upward into the air. And these back tires are over 2 meters tall, so if I stand next to them, they're taller than I am. Let's take a look at integration at NASA's Langley Research Center. This is in the high bay and clean room facility. You can see a clean room back here. This is our Pelican case that contains a lot of our tools. This case does go in this large crate. Here on the table, you can see that I am processing a lot of the cubes, tracking them, ensuring that nothing has leaked out, has spilled. Around the edges, we do put painter's tape to keep them contained, make sure nothing leaks. Especially if it gets hot during launch. And then here's our official crate that the carrier goes into. So this thing is pretty heavy. I have an extremely difficult time lifting it out myself. I can do it, but it's pretty much a 2-person job. This is another view of integration for RB5. I don't have all of the experiments in here quite yet. This just says, welcome to the 40-foot clean room. Here's my Diet Coke, which gives me power during these times. And this is my notebook that has been with me for every balloon launch since 2015. So all the notes about the experiments, the locations of the experiments, the manifests before I put that information into the computer, all contained in that notebook. It's seen a lot of spills too, so thank goodness it has a plastic cover. Here you can see that I do have one of the experiments. They do go into the spaces between this foam. This metal is the back plate. We call it Swiss cheese. It does have holes, so we do thread the wires and the switches through so that we can activate the powered payloads from the back and quickly, because we don't want to open up the case on the flight line because we have very limited time on the flight line the day of launch. Here's one of my favorite pictures that we have. This is our official crate. You can see our critical space system decal from NASA on the side, our cubes in space, our fragile sticker, or fragile, if you're a Christmas story fan. This travels from NASA Langley to New Mexico and back, and well, it's just pretty cool. Let's take a look at some of the requirements. Many times we're on the LDB test flight mission, but other times we could be on different missions like SIFT or WASP or RADX. We're typically on a 29 or 39 million cubic foot balloon. Bigger balloon, the more mass it can lift. And the campaign is the fall campaign, which launches August, September to early October in New Mexico from Fort Sumner. We really like to have a minimum of an 8 to 10 hour flight time with at least 5 hours in the stratosphere. We do want a good amount of time in a near space environment for the experiments to be able to gather enough data or be exposed to the conditions long enough for the students' experiment and research. We want at least 4 hours at float in a near space environment, so that gets us above 36 kilometers. We want to be outward facing on the gondola, and we do want to rotate. One year we were faced towards the sun the entire flight. It got terribly hot inside the carrier and melted a few of the cubes and fried some electronics on other experiments. So that was unexpected and not entirely what we wanted. The cubes will be outward facing, and we do like to have the wires be at least 40 centimeters in length and threaded through the back plate of the carrier. This diagram, NASA's balloon diagram, you can find in the airborne fact sheets in the content. You can also find it on NASA's Balloon Program Office website, but it does give you an idea of the size of the 39 million cubic foot balloon and a lot of details about the mass and volume. These things can be quite massive, and again, the larger they are, longer they can stay up, and also the longer that, or the more mass they can hold and lift. A quick slide to show locations from where NASA launches balloons: Texas, New Mexico, Sweden in Europe, Australia, New Zealand, and also Antarctica. So definitely go to NASA's Balloon Program Office website and check out more information, especially about the Antarctic campaigns each year. This diagram is pretty important, and you can find this type of diagram in most textbooks having to do with or covering Earth's atmosphere, looking at the temperature, pressure, and humidity profiles for the different layers of the atmosphere. This is really important that the students understand what is happening, because in the troposphere, notice that your temperature decreases as you increase with altitude, but then in the stratosphere, it increases again. It doesn't get super hot. It's just to about freezing at the stratopause. But all of these conditions are some of the independent variables that are going to act on the entities of the experiment. Other conditions we're looking at, radiation is something else to consider as far as an independent variable. And this pretty much ends this segment of the content for covering the specifics of the balloon. More content in several of the other courses, and we encourage you to check those out.